Okay, in this module, I'm going to start talking about metamorphism and metamorphic rocks. I'll define metamorphism, talk a little bit about different types of metamorphism, and then focus on subductions on metamorphism where we have high pressure and low temperature conditions. Then discuss metamorphic facies and metamorphic grade, and then a little bit about common mineral assemblages. Metamorphism is a subsolidus process. That means these are solid state reactions or changes to a rock with increased pressure and temperature. That means it does not involve melting. And you can think about the solidus on the phase diagrams that we've looked at for igneous rocks. These are processes taking place below the solidus, so at temperatures lower than are required for melting. Now, metamorphism involves changes in mineralogy or the texture of a rock, or both. So we might see changes in grain size, or minerals like hornblende transforming to pyroxene at higher temperatures. This can often involve changes in chemical composition of a rock, particularly if there are fluids that are coming in to help drive metamorphic reactions. The changes are due to physical and or chemical conditions that differ from those normally occurring at the surface of the Earth, and different from those processes that are taking place in zones of cementation and diagenesis. Diagenesis being those processes taking place in a rock after it's lithified, but before metamorphism starts. So very low temperature conditions where you might see changes in porosity, for instance. And metamorphic rocks can coexist with partial melt. Again, think back to that phase diagram from igneous rocks. There's that field below the solidus that contains liquid plus crystals. So the crystals would, in that case, represent the metamorphic rock, and the liquid being a partial melt of that metamorphic rock. So let me just emphasize, metamorphism is a solid state process. Melting is not involved. Now I'll describe the low temperature and high temperature limits of metamorphism. On the low temperature end, metamorphism is grading into diagenesis, and the processes are indistinguishable, but we can think about metamorphism starting about 100 to 150 degrees Celsius for more unstable protolith. A protolith is, as the name implies, proto is prior or earlier form of the rock, lith being a rock. So what the rock was before it was metamorphosed. So that temperature range is variable, and so there's a fuzzy boundary in the low temperature end of metamorphic processes, and I'll point to those on the pressure temperature diagrams. So some zeolites are considered diagenetic, and others consider them metamorphic. Zeolites, I mentioned this in class, some debate whether the feldspathoids are zeolites or zeolites are feldspathoids. So those are very low temperature minerals, and it's unclear, it's pretty arbitrary whether you call them diagenetic or metamorphic. And the high temperature limit of metamorphism, this is where we're grading into melting. And there's a range of melting temperatures for the different minerals. Just think about Bowen's reaction series. Those minerals like K-spar, quartz, those have much lower melting temperatures than do the hornblendes or the pyroxenes. Once melting has taken place, once the metamorphic rock has been melted, or some of it has been partially melted, you're left with perhaps xenoliths, so foreign rocks in the melt, or restites. Those are rocks that are left behind after you remove a partial melt, or other enclaves within the melt. And an enclave is like a xenolith, except that there's no indication, or it's unclear where that rock originated. And when you start to get partial melting in a metamorphic rock, that mixture of melt and rock is called a migmatite. And so it's a gradational process between going from metamorphic processes to igneous processes. Here's a migmatite, and what I want you to notice in the rock is the center of the image. We have what looks like a granitic gneiss. It's got a foliation, this planar texture. It is comprised of dark mafic minerals, and if it's granitic, we can say perhaps they're hornblende and biotite. And it has lighter minerals like quartz, case bar, sodic plagioclase. And then notice these former melt pods that are comprised of lighter colored minerals. Those are quartz, case bar, sodic plagioclase. And again, think to Bowen's reaction series. If you're going to take a granitic rock, heat it up to where it starts to melt, the first minerals to melt will be those that are lower on Bowen's reaction series. And that's what we're seeing in these veins. That's these quartz, case bar, and sodic plagioclase minerals. Now, we've talked about geothermal gradients before, and this diagram shows pressures and temperatures of for continental crust and oceanic crust, but we'll focus on the continental crust. And that's this zone in pink right here, where this is a range of conditions that are true depending on whether you're in the upper part of a continental crust or the lower part of a continental crust, and what temperature those rocks would be at a given depth. And I've just drawn in here at about 500 degrees Celsius to the middle of the continental crust. And that puts us at about 35 kilometers. That's the middle of the crust for the Himalaya, that is as thick as 70 or 80 kilometers underneath the high peaks. And perhaps mid-crust under the Sierra Nevada. It's a little bit deep for a normal section of the continent. So maybe that would be on the lower continental crust in this case. But the geothermal gradient then works out to be something like 14 degrees C per kilometer. That's pretty typical. You could round off, say 15 degrees C per kilometer. So in this case, in the lower crust or the mid crust, depending on where you're talking about, you're getting down to 500 degrees Celsius. And so these temperatures, this range of temperatures, are going to be represented in the metamorphic rocks that we're seeing, depending on how deeply the rocks were buried, how hot they got. Temperature is by far the most important agent of metamorphism, probably followed very closely by fluids, but we'll focus on temperature and pressure. As rocks are buried by various processes in the earth, temperature is increasing because of the geothermal gradient. And we're seeing changes to rocks like recrystallization. And I've given you an example here of a limestone recrystallizing into a marble. And you see how there's a grain size is coarsened over the course of that metamorphic process. That's one example. Temperature also drives reactions. And so it helps minerals to overcome kinetic barriers to transformation. And just as an example, down below I have an image showing an augite in the center of this grain, surrounded by a rim of this green hornblende. What this is showing us is in this rock, there was augite, and the pressure and temperature conditions changed, and hornblende started to replace the augite because it was more stable at those pressures and temperatures. So we see changes like this because of temperature changes during metamorphism. Pressure is important. We know that pressure increases with depth, and the normal gradient that you see in the crust can be perturbed depending on the tectonics of the region. So we see high temperatures and relatively low pressures where we have areas with plutonic activity, the heat coming from the plutons, or rifting, where we're thinning the crust and we have more conductive heat from the mantle getting into the crust. Or we might have an area of low temperature and high pressures, for instance, in a subduction zone. And I've showed you that before, where you drag down the isotherms and keep the crust relatively cool compared to the depth and pressures that it's at. And pressure is important too in determining what phase is stable. And I've mentioned this as well. In this image, we have brightly colored, or bright birefringence on sillimanite, and this more first order yellow color is kyanite. And in this case, the reaction that we're seeing is sillimanite replacing kyanite, reflecting a change in pressure temperature conditions. But pressure is important. Kyanite's the stable phase at higher pressures. Here's a typical subduction zone, and metamorphism is taking place in several places in this collision zone. We have in subducting oceanic crust, we're seeing conditions with high pressure and low temperature. In areas around plutons, those rocks are being subjected to high temperatures and not necessarily high pressures, maybe medium or low pressures. And then in the area within the mountain belt itself that's building up, we have conditions that are moderate temperatures, moderate pressures, and those are areas of regional metamorphism. So we see all of those. We see subduction metamorphism. We see what's called contact metamorphism around plutons. And we see regional metamorphism within a mountain belt. If we look at a pressure temperature diagram, you'll see on here different areas, and you'll notice the Franciscan that has this very steep slope with high temperatures at relatively low, high pressures at relatively low temperatures. Areas around plutons that are hot and not necessarily and are at low pressure, and then this region in between the two extremes where we have, and it's highlighted here, the Scottish Highlands, that are these regional metamorphic rocks at moderate pressures and temperatures. So we can label those as being, in general, reflecting high pressure, low temperature subduction zone metamorphism, moderate or medium pressure and temperature regional metamorphism, and high temperature contact metamorphism. Those are the three basic types of metamorphism that we're going to deal with in class. Now we focus on subduction zone metamorphism for now. A typical subduction zone, we have oceanic crust being subducted beneath a continent. And I've described metamorphic processes taking place within the subducting slab. And because it has this high pressure and low temperature regime for the subducting slab, we see the development of blue schists that are defined by the appearance of sodic amphiboles or glaucophane. We also, at higher pressures, we also see eclogite facies rocks. And those are defined by amphicite, a sodic pyroxene, and garnet. Now, the rocks are being transformed too and driving off water from the metamorphic reactions. For instance, the amphibole, the chlorite, those have the hydroxyl groups, and that water is driven off and enters into the mantle wedge above it and generates partial melting. We've talked about that. Not the slab that's melting, but the mantle wedge above it, when the water that's being driven off by the metamorphic reactions is lowering the temperature of the mantle itself. And we've also talked a little bit about the isotherms in a subduction zone. And this is a good image to show, if I just follow the 600-degree isotherm, that the relatively cool oceanic crust that was nearer to the surface is now being subducted, is dragging down that cool with it into the subduction zone. And that's really what's generating these high pressure, low temperature conditions for subduction zone rocks. This is a metamorphic facies diagram, and I've sketched this for you before in class. And there's a lot of information on this diagram, so let me just lay out a little bit of what you're seeing. You're seeing temperature increasing on the x-axis, pressure increasing on the y-axis. You're seeing an area highlighted in gray here at very high pressures and very low temperatures. It doesn't exist on Earth, and so no rocks are going to be represented in that part of this diagram. You're seeing trends for high pressure and temperature and low temperature subduction zone rocks. I'll abbreviate that. You're seeing a low pressure, high temperature trend for contact metamorphic rocks. You're seeing a sort of medium pressure and temperature series for regional metamorphic rocks. So those purple fields are showing you what pressure temperature conditions are represented in those various kinds of metamorphism. I showed you also in the last couple of slides that in subduction zones that they pass through blue schist and eclogite facies stability fields. So those are the pressure and temperature ranges that are appropriate for eclogite facies, for blue schist facies, and that regional metamorphic rocks are following a different trend. So those are passing through prehnite and pompelliite, green schist, and as the name implies with green schist, you're getting minerals that are green growing, chlorite, actinolite, epidote, that are stable over those range of pressures and temperatures. It passes across the amphibolite facies field, and as the name implies, at least as the name implies, hornblende is going to crystallize and be an important mineral. Granulite facies at higher temperatures. Granulite facies is characterized by pyroxenes rather than hornblendes because the temperatures are too high and the water's all been driven off as a rock passes from amphibolite to granulite facies. And down in the contact metamorphic zone at low pressure and high temperature, we're seeing hornfelses and sanidinites. These are rock names appropriate for different assemblages at those pressure and temperature conditions. You're also seeing this wet granite melting curve, and that is the curve of you're starting off, your protolith is a granite. It has some water in it, structural water. That's the temperatures that you must reach as you're increasing pressure and temperature conditions, where you'll start to see partial melting. And that curve is going to move to higher temperatures if your protolith is a basalt or some other rock that is more mafic than a granite. And this is where you're stepping over the liquidus and starting to get partial melts. The other thing I want to point out in this diagram that's important, we have these metamorphic facies that describe a pretty specific pressure temperature range for metamorphism. But if you were trying to describe in general the metamorphic conditions without getting this specific, you could say you have low-grade metamorphism at low pressure and temperature conditions. You could say you have high-grade conditions at high temperatures and high pressures. You could also say for regionally metamorphosed rocks, those are sort of intermediate grade. They're medium pressure and temperature. So this term, a metamorphic grade, just is really generic and applies just in a very broad way, conditions that are more extreme in terms of high grade metamorphic rocks or low grade at these low pressures and temperatures. So that's just a generic way of describing that. And also notice the one final thing, the zeolites down here at the low temperature end of the diagram. That's where this fuzzy territory where we're on the low temperature end of metamorphism, grading into diagenesis, and it's unclear exactly where you might draw that line. But certainly everything in this direction at higher pressures and temperatures is metamorphic. The final thing I'll say about high pressure metamorphism for now are just the mineral assemblages. The Granulite Facies being diagnostically having glaucophane, the Eclogite Facies rocks diagnostically having amphicite and garnet, but this is also specific to metabasalts, so metabasalts. You're starting off with a basaltic protolith. And these minerals that you're going to get in subduction zone rocks are going to be different if you subduct a granitic rock versus if you subduct a basaltic rock. So keep that in mind. The chemistry is different. So what you learned in this module is that metamorphism is a subsolidus process that changes the mineralogy and texture of rocks at temperatures above 100 to 150 degrees Celsius until you get to melting temperatures appropriate for your protolith. That there are different types of metamorphism, and I broadly discuss subduction zone, regional, and contact metamorphism. That subduction zone metamorphism has conditions that are high pressure and low temperature. The metamorphic facies describe a range of pressure and temperature conditions where you expect to see certain mineralogic changes. And that you can generalize about metamorphic grade of a rock by saying it's a low, intermediate, or high grade rock. And that depending on your protolith, you expect to see certain mineral assemblages depending on the pressure temperature conditions for the rocks. In the case of blue schist and eclogite, it's the diagnostic minerals of glaucophane for blue schist and amphicite and garnet for eclogite.